Hi guys, here in this lecture we are going to discuss important reactions of metal carbonyls. Just remember that if one learn the chemistry with great patience and concentration will become the master in chemistry. Okay, right, just come to the point of lecture. So here as in the part of important reactions of metal carbonyl, the first one we are going to study is the substitution reactions of metal carbonyls. So we can see the most important substitution reactions of metal carbonyls are divided into two categories. They are dissociative substitution reactions, and next one is associative substitution reactions. Okay, right. The dissociative or associative mechanism which is followed by the metal carbonyl depends on depends on metal carbonyl whether it is going to obey 18 electron rule or not. Okay, so based on 18 electron rule, metal carbonyls can decide dissociative mechanism or associative mechanism. Okay, right. Now just look at dissociative mechanism here. Almost all the metal carbonyls which obey 18 electron rule, that means which contain 18 valency electrons, will undergo dissociative substitution reactions. Okay, just note this important point. Now, so why 18 electron complexes are not undergoing or not simply involving associative mechanism in the substitution reactions? The reason is whenever 18 electron complex gets associative mechanism, for example, if a new ligand is adding to it, which is 2 electron donor, then what happens? Intermediate will get 20 electrons. Okay, we know that the 20 electron intermediate is energetically very high. That's why it is very unstable. So the formation of 20 electron intermediate is very unstable. So 18 electron complexes are not interested to involve in associative substitution reactions, whereas 18 electron complexes are readily involves in dissociative substitution reactions. Okay, right. Now just look at the first one, dissociative substitution reaction. Okay, just write down dissociative substitution reaction. Okay, right. Here just observe the general reaction here, that is metal coordinated with n number of ligands. So those ligands may be CO ligands or other ligands. Okay, right, but it should have at least one CO here. Now so with the rate with CO with a rate constant K1, and backward reaction is also possible with adding of CO with backward rate constant. Okay, just observe it in the next step. By lossing CO in the forward reaction, it produces MLN intermediate. Okay, in the next step, adding of a new ligand, then with the rate constant K2, it produces the final substituted product. Okay, so this is a general reaction we can observe in dissociative substitution reactions. Okay, right. And here the first step is rate determining step. Okay, that is the slow step and rate determining step, and second one is the fast step. So in rate determining step, that means that the rate only depends on concentration of the complex. Okay, so that's why we can express rate equals to K1 into the concentration of complex. Okay, right. But in some cases the backward reaction is also possible. Okay, that means adding of CO to the intermediate can also possible whenever the incoming ligand is bulk one. That is, if incoming ligand is sterically very bulk one, then adding of CO will also possible. So in that case, rate can be expressed as K1 into K2 and the product of concentrations of complex and the incoming ligand Y by the backward rate constant into the product of concentrations of a CO plus K2Y. Okay, so the first one for the forward reaction, and whenever backward reaction is also possible, we can use the second rate equation. Okay, right. Now the important concept here we need to look at. So in dissociative substitution reactions, simply what we see in the intermediate stage, the coordination number is decreased. Okay, for example, if we take a 6 coordinated metal carbonyl, then in the intermediate, by the loss of CO in the first step, it contains only 5 CO, that is coordination number is decreased by 1 in the intermediate, or most probably by just making a coordination with labile ligands. So example, tetrahydrofuran, and in the next step adding of new ligand takes place and we can get the substituted product. Okay, right, just take the general reaction here. You can understand why tetrahydrofuran addition is very important here. So just look at the reaction. MCO6, okay, hexacarbonyl is taken and reacting with tetrahydrofuran, right, and it is the first if in this reaction simply we can get the loss of CO takes place, okay, and coordination of tetrahydrofuran takes place. So you can observe this one. In the next step, which is reacting with next ligand, desired ligand we are going to add, that is triphenyl phosphine. Just think like that. Okay, now in that case, so the replacement of tetrahydrofuran by triphenyl phosphine takes place and the final product is simply we can get as PR3. So this is the dissociative mechanism we can observe, and adding of labile ligands. Okay, so these are considered as labile ligands favor dissociative substitution reactions in metal carbonyl complexes. Okay, just note this important point. Whenever we add labile ligands like tetrahydrofuran, that simply favors dissociative substitution reactions in metal carbonyls. Why they can favor dissociative substitution in metal carbonyls? You can see by just taking the complete information through the drawing. Okay, so you can see I'm just drawing the 6 coordinated metal carbonyl. Okay, right. So what is happening? So simply in the first step, CO is just cleared from it, and then adding of in the next step adding of tetrahydrofuran. So in that case, CO tetrahydrofuran. So just draw the complete structure of it. Okay, right. Now you can see tetrahydrofuran here. We know that tetrahydrofuran is a pure sigma donor. Okay, tetrahydrofuran is a sigma donor and very poor pi acceptor. So almost it is not a pi acceptor, simply sigma donor. And we know that whenever sigma or a sigma donor ligands are coordinated to the metal carbonyl, what happens? Due to their sigma donation, electron density increases around the metal. Okay, so whenever electron density increases on the metal, so metal is ready to back donate extra electron density towards electron accepting, that is pi accepting ligands. Here we have CO ligands. So whenever back donation is possible, then bond between metal and carbon of each metal carbon CO bond increases, but the bond strength increases. Okay, so due to the bonds increasing bond strength between metal and carbon, then which is the weakest bond we can observe in the given intermediate stage? Simply metal tetrahydrofuran bond will be the weakest one, because we can observe only sigma bond in between metal and tetrahydrofuran, but in between metal and the C carbons of all other we can observe extra interaction, pi interactions. Okay, that's why weakest bond is observed on tetrahydrofuran metal one. So just write down once again CO. So I'm just drawing once again. So tetrahydrofuran. So here weakest bond is simply tetrahydrofuran bond. That's why incoming nucleophile or simply incoming ligand simply replaces tetrahydrofuran, and from that we can get the final substituted product. Okay, here PR3. So that's why here the labile ligands favors associative substitution reactions in metal carbonyls. Okay, so here we have so many labile ligands, like here we can take examples CH3CN, okay, and all other like tetrahydrofuran and dichloromethane, okay, and other one is NBD. What is the full form of NBD? Narbornadiene, okay, NBD. And next one is we can take COT. So what is COT? Cyclooctatetraene. And next one, the labile ligand can be used in dissociative substitution reactions in metal carbonyls is COD, that is cyclooctadiene. So all these are labile ligands which favors dissociative substitution reactions in metal carbonyls. Okay, right, just take some important reactions here. I'm going to give chromium carbonyl. Okay, chromium carbonyl whenever reacting with 3 moles of MECN. Okay, so MECN, so simply I'm just taking MECN, MECN, then so sorry, just take 3 MECN. It produces CO3 and MECN taken thrice. Okay, so as we said, MECN or methyl nitrile ligand is a labile ligand. That's why it can easily replaced by next. I'm just taking triphenyl paspene, 3 moles of it, then the product will be C3 and PPH3. Okay, so this is the main dissociative substrate product can be observed by just using labile ligands. Okay, and just remember that here methyl MECN, okay, MECN always replaces 3 CO ligands. Just remember that important point, which will helpful for you to get the reactions in metal carbonyls. Okay, right, and we can observe so many of that here by just taking narbornadiene CrCO6, which is reacting with narbornadiene. Okay, right, in this case by the loss of 2 CO here, it produces CrCO4, and which is interacted with narbornadiene from the pi bonds of it. Okay, so like this, in the next step, whenever we use other ligands, triphenyl paspene is used, two ligands of them. And what happens? Simply due to the labileness of this ligand, triphenyl paspene is replaces narbornadiene and it produces CO4 and PPH3. Okay, so this is the major product. So here too we can get in this reaction. So labile reactions favors dissociative substitution reactions. Okay, right. And in the next important point we are going to check. So I'm going to give one question, that is when a metal carbonyl, that is octahedral metal carbonyl, is reacting with triphenyl paspene. Sorry, simply I'm just giving trialkyl paspene, 3 equivalents of trialkyl paspene. Okay, 3 ligands of trialkyl paspene. Then we under heating conditions, it is going to produce facial product and meridional product. Okay, then which is the major product we can observe in this reaction? Is it facial is the predominant one or meridional product is the predominant one? So just look at the mechanism here to know the major product in this reaction. Simply the first one, CO, here just draw the structure of octahedral metal carbonyl here, and in the first step trialkyl paspene is going to replace one of the CO. Okay, so we can just draw PR3 here. Okay, right. And now the point is, just look at PR3. So we know that trialkyl phosphine is a best sigma donor and poor pi acceptor. Okay, poor pi acceptor. That's why in the next step, adding another trialkyl phosphine. So just look at the trans bond, that is trialkyl phosphine and CO bond. If you observe this, so it is a sigma donor, right? So that's why electron density increases around the metal. So which back donates the CO? So the CO bond strength, that means, sorry, metal carbon bond strength increases here. So due to the increasing metal carbon bond strength, the incoming nucleophile cannot replace the trans CO to the trialkyl phosphine. Okay. Here we can simply say that the trans effect of CO is more than trialkyl phosphine. Okay, and in that case, the next nucleophile should be, or the next ligand should be replace CO other than trans CO to the here trialkyl phosphine. Okay, just take this, and here we can write PR3. And in the final step, simply another CO is replaced here, and we can get the product PR3. Now just look at here, here are the geometry of it. All the three trialkyl phosphines are same side and all the COs are same side. That's why we can say it is facial product. Okay, facial geometry of this product, and that's why facial product will be major one, and this is the predominant product observed in this reaction. So why not meridional? Already as we discussed, so to make them, so just draw the meridional geometry here. Okay, so you can understand it well. So here CO, and here trialkyl phosphine, right? And here is the CO, here is CO, and trialkyl phosphine, and you can observe this is meridional geometry. Okay, to get this meridional geometry, what should happen? One of the, here after forming PR3, one of the CO which is trans to that PR3 should be replaced by next nucleophile, that or next ligand trialkyl phosphine. Then only we can get meridional product. But already we have discussed that trialkyl phosphine is a sigma donor. That's why, which is strengthening the bond between metal and carbons of all the metal and carbons in the given intermediate. So it is very difficult to replace the CO which is trans to the already existed triphenyl phosphine in that intermediate. So the meridional product formation is very less when we compare with a facial product. Okay, so that's why here facial product is predominant one when we compare with meridional product. Okay, and another important point is the rate decreases by increasing the new incoming ligands. Okay, that is, for example, if when we use trialkyl phosphine, so here we are going to produce same. Okay, just draw once again CO and CO here, CO. And here I'm just taking PR3, two of them. That means after the first replacement or first dissociative substitution is very fast. Okay, but whenever we are going to add next trialkyl phosphine, what happens? Already due to the presence of first sigma donor, then the bond strength is increased here. That's why the cleavage of metal carbon bond will become difficult on further adding of next sigma donor ligands. That's why whenever we are going to add sigma donor ligands on metal carbonyls, the rate of dissociative substitution decreases. So this is the one point. And next point is, whenever we look at the bulkness of the ligands, so bulkness of the ligands can also play a role in which determines rate of the dissociative substitution reactions in metal carbonyls or and other compounds. For example, here just take nickel with trialkyl phosphine as the ligand. Okay, and which is having cone angle. So cone angle is 118 degrees. Okay, whereas next one I'm just taking other ligand, so that is here tertiary butyl substituted phosphine. Okay, so here if this one, if you look at the bulkness of this, the cone angle become 182 degrees. So what is cone angle? Simply in tetrahedral geometry you can take, so this is the cone angle, you can see 3 PR3 here, PR3 and PR3 here, PR3. Okay, just you can see this is cone angle. Okay, so this is cone angle observed in it, and the cone, whenever cone angle increases, then a dissociative substitution increases. Okay, so just note that important point here. Okay, right, and in the next step we can also see that whenever amines, whenever we observe the ligand amine, so I'm just taking an trimethyl amine, okay, with metachloroperbenzoic acid. So whenever we observe the combination of this, which accelerate dissociative substitution reactions in metal carbonyls. Okay, why it is increasing or just accelerating dissociative substitution in metal carbonyls? So that is just due to, so whenever we observe pyridine is reacting with metachloroperbenzoic acid, it leads to produce N-oxide product. Okay, so this N-oxide going to attack on, so here the one of the CO, okay, one of the CO of metal carbonyl, and in that case which improves, okay, that means which accelerate the dissociative substitution. Okay, and that's why here whenever we use amines with a combination of metachloroperbenzoic acid, the dissociative substitution increases in metal carbonyls. Okay, just try to check the complete mechanism here, right? Thank you very much.